Hello, and welcome back to another episode of Data Model Design Interview Series. In today's episode, I'm going to cover most frequently asked questions in data model design. And let's start with normalization. So, what is normalization? It is a database technique used to organize data in relational database efficiently. It involves breaking down a single large table into smaller related tables and defining relationships between them to reduce redundancy and dependency. And the main goal of normalization is to eliminate data anomalies such as insertion, update, and deletion anomalies. So let's look at an example and understand what is a normalization and how many different types of normalizations we have. So we have this employee table with employee ID, name, and the department. And even in department, we have multiple departments. And for project, we have multiple projects, project A and project B. So for the first normal form, so what is first normal form? A relation is in first normal form if it does not contain any repeating groups or nested fields. So for this example here, it has repeated groups for department and even for projects. So in order to convert that to first normal form, this is the condition here. A table is considered to be in first normal form if it does not contain any repeating groups or nested fields. An example here is each attribute value must be atomic, meaning it cannot be divided into smaller pieces. And if you see here, this employee table, after it got converted to first normalized form, employee ID 1, name Alice, she belongs to HR department, and for project A. And again, for the same employee, for the same name, for the same department, we have project B. And again, I think I missed two other entries here, but the same employee ID, same name, we have engineering and which belongs to project A, and same engineering which belongs to project B. So there should be two more entries here. And likewise for the other employees too. So now this table is considered to be in first normal form. Let's look at the second normal form example. So what is second normal form? A relation is in second normal form if it is in first normal form and every non-prime attributes is fully functionally dependent on the primary key. So let's take this one as an example here. So for the employee table here, the project description attribute is functionally dependent only on the project ID. So this project description is functionally dependent only on project ID, which is part of the primary key. So here in this example, primary key is employee ID and project ID. But this project description is dependent only on the project ID here and not on the entire primary key, which is employee ID and project ID. So in order to bring this table into second normal form, we have to remove this partial dependency by separating attributes into two tables. So now we have employee table, which defines like employee ID and name and maybe some other details related to employee. And now the project table will contain project ID, project name, and description. And now we can have another table which gives us the relationship between employee and project, which is employee ID and project ID. So this is how we'll consider a second normal form um, tables here. And the third normal form. And the definition is a relation is in third normal form if it is in second normal form and there are no transitive dependencies. So what is transitive dependency? Which means non-prime attributes should not depend on other non-prime attributes. They should depend only on primary key. So let's take this one as an example. We have employee ID, department, salary, and department location. So in this example, department location is functionally dependent on department. So this location is dependent only on the department here. So if department is HR, its location is in New York. If department is engineering, its location is in San Francisco. So to bring this table into third normal form, we need to remove this transitive dependency by separating attributes into two tables. So now we have employee department relationship here. So this employee, he belongs to HR department and that HR department, it belongs to this location. And now we have employee, another employee salary table. So that employee will have this salaries here. So now, depending upon the use case, there is no hard and fast rule like we have to use only first normal form or second normal form or third normal form. Depending upon the use case and depending upon other factors like uh, where is that we are going to use this table and what will be the limitations in our project, like what will be the storage limitations or the performance limitations. Based on that use case, we'll be using any kind of one of the normalization method here. Like, so there is no hard rule like we have to go with second normal form or third normal form. And let's look into another concept called denormalization. So what is denormalization? Denormalization is the process of intentionally introducing redundancy into the database design to improve the query performance by reducing the needs for joins and speeding up data retrieval. So normalization will be kind of like, maintaining our tables and relationships in a clean way, much more like, no need to maintain or everything in a single table. We can just maintain IDs and another detailed tables will be having information about like employee or some department. On the other side, denormalization is more kind of using information in a single table and the use cases is like the fast retrieval of that data. Let's say we are using the table for some querying purpose in a reporting dashboard. um, we cannot join three or four tables there and do that complex logic of joining with all the keys and then provide that information on the front end of the dashboard. And in order to avoid that performance issues, most of the time, the tables will be in the denormalized way when we are querying for the reporting database. Let's take an example here. We have customer table, order table, and order detail table. So in normalized schema, order table serves as a junction table to establish many-to-many relationship between orders and products. However, retrieving information about customers' order and the products they have purchased may require joining multiple tables, which can impact query performance. So, in order to find out, let's say, uh, from customer orders, we want to find out what kind of products he purchased and what is the product information and what is the product category. So, we have to do a join between customer table, order table, and the product table. As I mentioned, in normal, if you are designing that table, yes, we have to go with that normalization format. But for querying purpose, if we are maintaining three different tables here, we have to join those three tables in order to get the information, and that information will be provided at the front end. So there is no kind of latency. There should not be any latency. And again, depending upon the business use case, if the latency is very minimal, we have to go with the denormalization method. So how is that we are going to uh, convert these tables into a denormalized way? So to denormalize this schema, you might introduce redundancy by including additional columns in the order table that directly reference customer and product information. So now the order table will have order ID, customer ID, order date, customer name, any information related to the customer, and also any information related to the product itself. So everything will be maintained in the order table. So now there is no need to join customer table and product table to get customer information and product information. So in this denormalized schema, customer and product information is duplicated in each other, eliminating the needs of joins when querying order data. So while the denormalized design may lead to increased storage requirements and potential data inconsistencies, just like it's some duplicate information, it can significantly improve the query performance, especially for the reporting and analytical queries. So that's the purpose of denormalization. Let's move on to the next topic, slowly changing dimension. So what is slowly changing dimension? A slowly changing dimension is a dimension in the data warehouse that changes over time. It will not happen more frequently, but it will happen at a like at a frequency. So for just an example sake, we have customer table and we have customer address. So customer address will not be changing every single day, but at some point in time, customer address might change. So that's an example. We'll call that as a slowly changing dimension. And what are the types of slowly changing dimension? So we have three types: SD1, SDC1, SDC2, and SDC3. So slowly changing dimension 1, uh, the method which we use to overwrite the existing record, let's say the customer address is changed. So now we'll just go and change his customer address without maintaining any of his previous or historical data. So that is called overwrite or SDC1. And the second type is just add new row. So instead of changing the address of the customer, we'll just keep that existing row as it is, and then we'll just add additional row there. And the third one is add new attribute. So rather than adding a new additional row here, in the slowly changing dimension 3 method, we'll just add one more column to the table, and we'll maintain just like uh, previous address and current address. Let's say customer address, it has changed 5 times in his entire record in that database. We'll still maintain the fourth record and the fourth address and the fifth address, which is the current address. So that's the SDC3. Quickly, we'll go over the examples here. Um, Explain S1 SD type 1. So the old dimension table is simply overwritten with the new data. An example is customer dimension table where customer address is updated. So type 1 SDC is old address is replaced with a new address. And type 2 will be new row is added to the dimension table to represent the change while the existing row remains unchanged. This allows the historical track of the changes. So we have the old record as well as the new record. So whenever we want to know what is the latest address of this customer, we'll have something like we'll extract with latest date or the highest date. So that will give us the latest address for that customer. And for type 3, additional columns are added to the dimension table to track the specific changes, such as previous and the current ones. Only a limited amount of historical data is retained. In the example I have provided, we are maintaining only two levels, or the current previous address and the current address. And again, if we want to maintain the third one, we can say like previous one address or previous address and current address. So we can always go back and define at what level we want to maintain that information. So that is all about SDC, slowly changing dimension. Let's talk about another concept called surrogate key. So surrogate key are artificial primary keys used in the database instead of natural keys. So let's take an example here. So let's take an example of customer. So customer usually, like, when we say customer, we can think of his customer first name, last name, his address or email, phone. But when we say the customer ID here, that's the surrogate key, which will be system generated key. So we know exactly using this customer ID, which is a system generated ID, we can identify the customer table particularly for that customer. So surrogate keys are used when there is no suitable natural key available, when natural keys are subject to change, or when the composite keys are too complex. So we can still identify customer with first and last name, but that's way more complex than having a surrogate key, which is a system generated key. So I just wanted to touch base, like, what surrogate key, and even though we use this all the time, the customer ID or product ID, or let's say some kind of ID, whatever is the system generated one, which is much more flexible to use, that's the surrogate key there. Let's look into the star schema. So what is star schema? A star schema is a data warehouse schema consists of one or more fact tables connected to multiple dimension tables in like star-like structure. So star schema are used in data warehouse environments for online analytical purpose, which is OLAP applications, where performance and simplicity of querying are crucial. Let's take an example of star schema. So we have the components of star schema is fact table. So what is a fact table? We all know what is a fact table. It contains quantitative measures, and dimension table says like we have some descriptive attributes there. primary and foreign key relationships, which can connect the fact tables and the dimension tables. And this will be much more denormalized way. When we say denormalized, it's still a normalized, but when it compared to Snowflake schema, this is kind of denormalized structure because that provides fast query performance for analytics. So on the other hand, for the Snowflake schema, it's a data warehouse schema where dimension tables are normalized into multiple related tables, forming a shape resembling a snowflake. This is an extension to star schema. So again, this will look like star schema, but again, in star schema, the tables will be a level of denormalized structure, but for Snowflake, it will be much more normalized way. So that is the difference between Snowflake schema and star schema. And let's look into the what are the advantages of Snowflake schema. The advantages of Snowflake schema include reduced data redundancy, improved data integrity, and easier maintenance. And disadvantages is obviously um, whenever we are trying to join, we have to join all the normalized tables there, which will be slower, potentially slower query performance and increased storage requirements. So provide an example of Snowflake schema. Just consider a star schema with a product dimension. In Snowflake schema, the product dimension table may be normalized into multiple tables such as product, product category, product subcategory, forming a Snowflake-like structure. And let's look into another example, data partitioning. So what is data partitioning? It is the process of dividing large tables or indexes into smaller, more manageable parts called partitions. And we have different kind of partitions, such as range partition, list partition, hash partitioning. So where is that we are going to use the data partitions? Data partitions is used to improve the query performance, simplify data management, and increase scalability in databases with large tables. So whenever we are dealing with huge volumes of data, we are going to partition that table based on some key. And we need to understand what kind of key we are going to create the partitions. So it can be on a date, or it can be a range partition, or a list partition, or hash partition there. So let's look into the example of range partition. Range partition involves dividing data into partitions based on specific range of values, such as dates or numerical ranges. Each partition contains data falling within that defined range. So if we define a partition, let's say on date, so each date uh, for March 25th, whatever data we collected, that will be on partition March 25th partition. So whenever in where condition we provide, like let's say select star from our product table, where um, date or product added date is equal to March 25th, it will directly go and hit that partition and get all the required information from that partition. And explain what is list partitioning. So list partitioning is another kind of partitioning where, like, even after having our range partition, sometimes, like, even after partitioning on date range, we'll be still having huge volumes of data. So again, maybe we need to go back and look into the data to see, like, um, can we have furthermore, like, drill down, we can have one more partition on that date itself. Maybe we can have some list partitioning. So here in this example, let's take a product database, a table called list partition based on product categories. So let's say we still have the product data, and which is partitioned on date. And again, we have a list partition on product category. So which category this product belongs to, electronics or clothing or some books related. So based on that list, we can still have the partitions defined on that table. And another kind of partition is hash partitioning. Hash partitioning involves dividing data into partitions based on hash function applied to one or more columns in the table. The hash function distributes data evenly across partitions based on the hash value. So here in certain examples, like where date partition or whatever partitions we define, we were discussing here, if that one is still not solving our problem, we'll just go with hash partitioning. So each row will be kind of each row will be partitioned based on some columns and then some hash values generated, and all the relevant hash partitions will be stored in one partition. So based on the hash value or hash function there. So just to provide an example of hash partitioning, in user database, the table can be hash partitioned based on the user ID, where the hash function evenly distributes users across partitions based on the hash value of their ID. So what are the benefits of data partitioning? The benefits of data partitioning include improved query performance, reduced storage and maintenance cost, simplified data management and increased scalability. So this is the generic method, or this is, we can expect questions on data partitioning either in data model design interviews, or the other side, we'll call that one as big data architecture interviews. So it can be the combination. So in certain interviews, big data architecture itself covers the data model design, or in certain interviews, data model design is a separate interview and big data interview is a separate interview. We can expect data partitioning question in both of these interview series there. And one more important topic, when they talk about partitioning, definitely they will ask a question on indexing too. So what is indexing? Indexing is the process of creating data structures called indexes on tables to improve the speed of data retrieval operations such as select, update, delete, and merge queries. So when is indexing used? It is used to speed the data retrieval operations, especially for large tables, by allowing the database engine to quickly locate the rows. So so just an example here, like let's say we are querying a product table, and we are mostly querying, let's say, a product category called clothing. So now we know, like, we are going to have a where condition on the product type. So most of our queries will be on the product type. Either it can be clothing or electronics or books. So we know most of our queries are taking the product type, so we can create an index on the product type there. So so by creating the index on product category, whenever we have a query, it knows exactly the index is created on that one, and that will retrieve those rows with wherever our index is created. So that will be a easy data or rows retrieval there. And what are the different types of indexes? Usually it includes B-tree index, bitmap index, hash index, and full text index. So let's consider a B-tree index example here. We have a table, product ID, name, category, price, and stock. Now let's say we frequently run queries to retrieve product information on the product category. To optimize the performance of these queries, we create an index on category columns. So we just create index on the product category. So we have the category column here. We created the index name category on products category. With this index in place, the database management DBMS creates a separate data structure that maps each distinct category values to the corresponding rows in the product table. So when we query that involves filtering, sorting, or joining based on the category column, the DBMS can use the index to quickly locate the relevant rows without having performed a full table scan. So now it creates an index on category, and let's say all the books category, it will have a data structure or some map on the each row for that books. And similarly for electronics, similarly for clothing. So whenever we query on a distinct category, let's say where my category is equal to books, it will directly go and fetch those rows because there is some mapping logic happening to retrieve just that category there. So that's the indexing method there. So for example, consider the following query to retrieve all the products in electronics category. So now where the category is equal to electronics, and since we have the index on category, it will internally map all the rows where the category is equal to electronics in one data structure there. Let's try to understand the difference between partitioning and indexing. It's not exactly the difference, but what is that both are contributing to our scalability and performance improvement. How we can compare, like, uh, where is that we are using partitioning, where is that we are using indexing, or where is that we are having a combination of both. Partitioning and indexing are both techniques used in database management system to improve performance and manage large data sets efficiently. But they serve different purposes and operate at different levels within the database. Let's start with partitioning. Partitioning involves dividing a large table or index into smaller, more manageable pieces. It's primarily used for improving manageability, scalability, and performance by distributing data across multiple storage devices. Whereas for indexing, it involves creating a data structure that allows for efficient retrieval of rows based on values of one or more columns. It is used to improve the performance of select, update, delete, merge operations by enabling the database to locate specific rows quickly. And another one is partition allows data to be distributed across multiple physical or logical storage units based on the predefined criteria such as range of values or hash functions. Each partition operates as a separate unit, enabling parallel processing and improving input-output performance. So let's say we have this different, let's say we have this partition on dates. So now if you want to retrieve data from March 25th and March 20th, it will, since every partition is logically stored separately, we can go and do um, the query retrieval in parallel, because every logical storage is independent. So we can just work in parallel to improve the input output performance. Indexes are data structures that provide quick access to rows in a table based on the values of one or more columns. They store pointers or references to the corresponding rows. So this is not, index is not a logical storage. It will just like map or store pointers or references to the corresponding rows. And partition is applied on the table of index, dividing data into distinct partitions based on the partition keys, whereas index are created on specific columns. And the other one is partitions can improve query performance by enabling parallel processing, and index can significantly improve the query performance by reducing the number of rows that needs to be scanned. So instead of doing a full table scan, if index is created only on that particular index, it will retrieve that rows. So which leads to faster data retrieval and query execution times. So in summary, partitioning and indexing are complementary techniques used in the database system to enhance performance and scalability. Partition focuses on the data distribution and storage management, while indexing targets efficient data retrieval and query processing. So both techniques play a crucial role in optimizing database performance for different types of workloads and use cases. So I just came up with most frequently asked interview questions in uh, uh, this data model design. So these questions I faced in my real interview. So I came up with this questionnaire. There can be more, but usually these at a very high level. These are the common questions which they will be asking. Hope this session is useful to you, and thanks for watching this video.